Now let us look at the memory structure, that is, which is part of the instance. So this memory structure is used, these memories are used to store program code, the SQL text and its parsed version, which will be shared by other users and sessions as well. It stores about the information about the connected session, at which point of that program is that particular session, and while it is searching through the tables, searching through the cursors, it just has to know at which record, at which point that particular session is waiting, so that it can do the next. It can start from that point. It stores the state and status of each program execution, whether that session or the program is active or it is inactive, how long it has been inactive, those kind of statuses. Then information which has to be shared with other Oracle processes. This is what makes the Oracle a multi-process, multitasking database. Data blocks read from the data files, that I think I have been reiterating for 2 or 3 times by now. So the data blocks which reads into the database buffer cache, and the memory which is shared by all users, background processes, is collectively called as a system global area. This is the shared pool, the database buffer cache, redo logs, all are which helps the background process and the server processes. They all grouped together as system global area. There is another memory which is very specific to the user or individual processes. A background process would have to keep some private memory to its own. So those memories are called as program global area. So there is a distinction between SGA and the program global area. Program global area memories are not shared. They are out of the system global area. When it is required, this program area will be acquired. This is a typical Oracle memory structure. Here you see the shared pool, Java pool, the large pool, and the database cache, and the redo buffers, and each of the server process, Oracle process, background process will use a little bit of the private memory in the PGA, and then they access the system global area, which constitutes all these memories. Shared pool is where the data dictionary is stored, and all your parsed SQL and SQL statement, the program status, the log information, all these things are stored in this shared pool. And the database cache is where all the data blocks comes and resides. This is purely used only for the data block caching, and it not used by any other functions. Java pool, after 8i, Oracle introduced Java into their database, and the JVM and Java programs run in this Java pool, which resides inside the database, which is inside the database. This is what makes the Java programs run faster in Oracle. That's why many people prefer Java on Oracle database. Then comes the large pool. Large pool is used for backup functions, like the RMAN, the backup tool provided by Oracle, uses this large pool. And redo buffer is used to redo the transaction in case of failures or recovery scenarios. So this is the structure. Now let us look at each of these components. Shared pool. The shared pool contains two main components: the library cache, which caches SQL statements and its parsed version. Okay, library cache. we have dictionary cache. See, dictionary cache is part of this shared pool. So what happens is, like, see, Oracle also has to keep an index of where things are lying around in this memory, these memories. Okay, so what it does is it creates a metadata. Like, take an example of when you are creating a table. The table, it spawns across extends, it spawns across blocks. So the dictionary cache has to keep a note of where it is lying, like a table. What is the structure of the table, like what are all the columns and what is the related indexes. So all those informations are stored as internal system tables in Oracle data, in the Oracle database. But when the database is started and it is functioning, those information also has to be brought to the shared pool for faster access and a proper functioning. Okay, faster access. So that is what gets stored in the dictionary cache. This is a small example which I am telling you, but there are a lot of other informations which are stored in the dictionary cache, such as information about users and tables. It also contains information about running processes like user, background, server processes, logs, etc. Okay, now let us look at the second component, is the buffer cache. So buffer cache keeps copies of data blocks which is read from the data file. All user processes can simultaneously connect and share this buffer. Blocks are always read and written in sizes of the Oracle block size, which was defined when the database was created. All these individual blocks of memory are indexed in two lists: LRU lists, that is least recently used list, and a dirty buffer list. As soon as somebody writes to a data block buffer, somebody changes something, immediately that block becomes dirty and it is ready to be returned to the database or to the data files back. Okay, the LRU list just forms the blocks which are read from the data file and kept for future reads. So what happens is, the most recently used or the frequently used blocks move to the top of the list, and the blocks which are least used moves to the least recently used at the end of that list. So that what happens is, whenever a new block is read and it is required a new memory, fresh memory is required by the fresh blocks, then the least recently blocks will be replaced. So the free blocks of memory are in the LRU list. If there is no free blocks left, Oracle writes the dirty blocks to the disks and frees up the memory, ready to be filled again from the data files. So you need to understand this LRU list and the dirty buffer list, how they are handled. The next memory structure is the redo log buffer. It is a circular buffer which holds information about the changes made to the database. Why they call it as a circular buffer is because it gets overwritten. That is, when it starts, then it comes back, there is not enough memory, it just overwrites changes made to the database. These information is stored as, the information in this log buffer is stored as redo entries in this buffer. Changes to the database by insert, update, delete, create, alter, or drop are recorded here. Even the commands like alter table space, alter any structural changes to the database or to any of its internal structures, the table structures, or everything gets recorded in this redo log buffer so that we can reconstruct the database as it was earlier during a recovery scenario. If required, these redo entries are used for database recovery. When it is full, the background process log writer writes the buffer to an active online redo log and frees the buffer for recording the next change. That is, it writes to the online redo logs. Now we saw the physical files, physical structure. We looked at the memory structure. Now let us look at the process architecture. This is what stitches all the pieces of the physical files at the memory structure. This process architecture is what stitches them together and serves the user as a database. All these three things have to work together to give you the service, provide you the service of a database. The process can be divided as user process and the server process, and some of the server process are also called as background processes. User processes which runs the application are one of the Oracle tools. The processes runs database server code, which can be a server process or a background process. A user process is created every time a user connects to the database. A user process is created every time a user connects to the database. In a shared server configuration, many user sessions can share a single server process. This server process parses the SQL reads the required blocks from the data file if it is not present in the buffer and returns the results back to the user. The user process connects to the shared server process, and that server process does all the job for you, like providing the data blocks to you, providing the required information back to the user. Coming to background processes. To improve the performance and to serve multiple users, Oracle uses additional processes called background processes. They do several other tasks in the background while you are performing your activities with the database. Some of the background processes are database writer, log writer, checkpoint, system monitor, process monitor, and then archiver, and some other background processes. The newer versions of the database have incorporated many more processes which we can cover later in the due course of the training. I will get into each of this in the next slides. DB writer writes the content of the buffers to the database. Depending upon the load on the database, we can configure more than one DB writer. DB writer writes the content of buffers to the database. Depending upon the load on the database, we can configure more than one DB writer. When there are more blocks, when the database becomes bigger and bigger, then your database cache will become bigger and bigger. So you might have to write back. There will be lot of writes onto the onto the database, so the buffer sizes will, the dirty buffers will increase. So to handle those kinds of loads, we can add one more DB writer, so that the database can quickly write back to the database. If we do that, then the part of recovery also will be easy, faster. Now coming to log writer. Log writer writes the redo entries from the redo buffer to the online redo logs. It can start the write process when a user commits a transaction, when the buffer is 1/3 full or every 3 seconds. The logic of a log writer is when a transaction commits and the buffer is 1/3 full or every 3 seconds, whichever comes earlier. When a user commits a transaction, the transaction is assigned a system change number and is recorded in the redo log. The system change number is what keeps track of the transaction. It sequences the transaction. Earlier system change number identified transaction has to be applied to the database after the next system change number. So it tries to sequence the transaction. This is a very important concept. The system change number is a very concept to understand the database recovery process, and how the transactions are recorded into the database, and while recovery, how this number helps in restoring the database and is recorded in the redo logs. Checkpoint process updates the headers of all the data files with the checkpoint details. This is once these headers of the data files are applied along with the control files, which this information is what is used while you start the database to find out if the database is in a consistent state and a recovery is not needed to bring the database back to a consistent state. The checkpoint process it should frequently update the data files and the control files, and after if we have done a proper shutdown, and then when we start up, and if all the headers in the data files complies with what the information is there in the control file, is when Oracle knows that the database is consistent. SMON performs recovery at the instant startup time if required, and is also responsible for some housekeeping on behalf of terminated process in SGA, and also cleans up temporary segments when it is no more in use by any active process. Sometimes the user processes can get terminated, or if it fails, but all the resources which it was holding on to, some of the memory structures or anything which is holding and has not been properly cleaned, will be lying in the memory, and the memory has to be very efficiently used because it's a scarce resource. So to optimally use the memory, this SMON will go and check for all these defunct memory segments and cleans them, so that the next processes can use them very efficiently. The database can run very efficiently. Also, once you finish the sort operations, the segments still lie in the temporary segments. So when a new sort comes in, if it doesn't find the temporary segments, SMON takes care of cleaning up the temporary segment and give free temporary segments for the new processes to function. PMON performs process recovery. When any user process fails and it is responsible for all the housekeeping activities on behalf of failed process and transaction which it was trying to perform. Archiver process, which copies the online redo log files to any configured device after a log switch. Archiver process copies redo log files to any configured device after a log switch. That means whenever the online redo log files are finished recording, that particular redo log files has to be archived to an archive logs. That is only when you enable archive log on the database and you need to recover the database days behind, for days behind, like say 3 days or 4 days past. And that archiver process can be configured to either onto the disks or to any devices like tape or optical devices, as the case may be. If the load is high, multiple archiver process will be started and the start will be recorded in the alert. The start and the end of the archiver process will be recorded in the alert log file. If you want to see whether the archiver is performing its function, it's better to look at the alert log file and you can find an entry in the alert log file. Now that we have seen the data file, the physical structure, we saw the memory structure and the process which stitches all these things together. But if there is any issue or you want to know whether all these are performing to their optimal level and they are without any hitches or without any issues, by default Oracle writes these activities, these intermediate status of these intermediate activities onto certain files, and also you can enable them by enabling certain parameters to dig further, or you can say that okay, give me more information from what has been collected by default. These informations are recorded in many different files. These you have to be very careful in enabling these traces, because they might fill up the disk space very quickly. So these are called alerts and trace files. Alert log is one of the important log files which records from the startup of the database all the redo log switches, all the SCN numbers, and if you perform certain activities in the database, certain alert alter statements, those statements are recorded in the alert log file. So each server and background process creates its own trace files. They can provide the cause of the failure and in some cases provide guidance also. It can help in doing the root cause analysis of the database. If once the failure has happened and the database had gone down, and then you restart the database, but you need to find out what was the cause of the failure. So you can go back to these trace files and the alert logs and see what could be the cause of the failure and you can give a root cause analysis of the failure. In some cases they provide guidance also what can be done to fix the issue. Even while the database is running perfectly, the users uh, might be doing their work very comfortably, but still there might be some warnings, informations returned to these alerts and trace log files, which you can monitor to uh, proactively monitor these files and can avoid certain downtime situations. So if you leave it if you don't observe those and just leave it, there could be a chance where your database can go down. So proactively monitoring of these alerts and trace files are one of the important jobs of a database administrator, Oracle database administrator. These alert logs sequentially, date and time wise, like you can it will be like an history of the database from the start till the shutdown of the database, and again when you start, that also gets recorded. So you can have all this information from the alert log file. Alert log sequentially, date and time wise, records what has happened in the database with errors, warnings the database encountered. Has happened in the database along with errors, warnings the database has encountered. Some admin type activities is also recorded in the alert log. When any admin type activity is completed, that also gets recorded